Greetings again, Astronomy 10. Welcome back to Chapter 2, Part 2. We left off last time talking a little bit about the imaginary construct known as the celestial sphere. The thing that doesn't actually exist, yeah, that. But it's useful to us because it's a good tool for understanding or visualizing the way that the objects in the sky appear to move around us, even though it's actually us, the Earth, that's moving, right, relative to everything else, and that gives us our changing perspective. So we already talked a little bit about how the stars appear to rise and set, and so too does the sun. But the sun's motion across the sky is just a little bit different from the very far distant background stars, and indeed just about everything else in the sky. Why is that? Well, it's because we have not one but two motions relative to the sun. So the Earth rotates, right? It turns day into night and so on every about 24 hours, right? It makes one complete revolution. But that's not the only thing it does. The Earth doesn't just rotate, it's also moving around the sun, right? Or revolving about the sun, right? So the sun has two major kinds of motion, or the Earth, excuse me, has two major kinds of motion. It rotates on its own axis, it spins, but it also revolves around the sun, making a big loop that's actually very close to a circle. It's about 1% different. Our orbit is very close to a complete and perfect circle. Now, how long does it take for the Earth to make one orbit, one trip all the way around the sun? What do we call that? Usually we call that a year, right? How long is a year? Don't say 365, because every 4 years we have a leap year, right? So every year is about 365 and a quarter days. It's actually about 365 and a quarter and 10 minutes. And that extra 10 minutes makes up, I believe, the Gregorian calendar corrections. But that's neither here nor there. Let's not worry so much about the tiny little details. And suffice to say that the sun is far enough away from us that it takes, or we're far enough away from it that it takes 1 year or 365 and a quarter days to revolve all the way around it. Now, that means that in 6 months, the sun is going to be on the opposite side of us at this time of the day. Right? It's a little funny to think. But as a matter of fact, it's true. We revolve around the sun, and so in 6 months, the sun is going to be in a very different place in the sky. And as a matter of fact, it's going to look like it's in a different place on the celestial sphere, right? As we move all the way around to the other side of the sun, it's going to look like the sun is in the middle of a bunch of different stars 6 months from now, just like it did 6 months ago, and 6 months before that, and so on. And so as we revolve around the sun, the place that the sun occupies on the celestial sphere, where all of the stars are, is going to be different, right? The sun is going to appear to move across the celestial sphere as we move around it. Crazy, right? But it really makes a whole lot of sense, and the images that go along with today's lecture should illustrate that pretty well. Now, essentially, the path that the sun takes across the sky looks like a circle. The circle that the sun appears to take across the sky is called the ecliptic. And that is also synonymous with the plane of the sun's equator. Interesting stuff, right? Now, if it takes 365 days for us to move around the sun, that means it takes 365 and a quarter, days, for the sun to move all the way around this ecliptic back to where it was, right? Because the sun's position appears to change as we move around the sun. So, how far across the celestial sphere does the sun move each day? Well, there are 360 degrees in a circle, there are 365 and a quarter days in a year, and so the sun essentially moves just a little less than 1 degree per day across the ecliptic. Interesting, right? And so if you look at a map of the positions of where the sun is at various times in the year on the ecliptic, you can kind of see where it is relative to the background stars that it's, not letting us see. Obviously, if the star is in some portion of the sky, we're not going to see stars over there, because when the sun is in the sky's blue, right? We don't get to see stars during that time of the day. Okay, in any case, the Earth's orbit is almost perfectly circular, like I mentioned before. We have about a 1% orbital eccentricity, meaning it's elongated, stretched about 1% from a perfect circle. And so this sun moving about 1 degree a day across the ecliptic is pretty money. It's pretty right on, pretty close. So that is how the sun moves across the celestial sphere. Now, because the sun appears to move this way, and the Earth's axis is tilted 23.5 degrees, there is part of the year where the northern hemisphere, where we are, is pointed towards the sun, and part of the year where the southern hemisphere is pointed towards the sun, or the northern hemisphere is pointed away from the sun, if you want to think of it that way. Why is that? Well, if the northern hemisphere is tilted 23.5 degrees toward the sun, then the sun is going to stay in the sky longer, right? And it's going to go higher in the sky if you live on the northern hemisphere. And as a result, here in the northern hemisphere, we have summer during those months when the northern hemisphere is pointed toward the sun. Now, strangely enough, contrary to what lots of crazies will try to tell you, the Earth is actually about 1.5 million kilometers farther away from the sun in the summer. And we're actually about 1.5 million kilometers closer to the sun in the winter. But we have fewer hours of daylight because in the summer, the northern hemisphere is pointed towards the sun, and then the Earth is over on the other side of the sun, and then the southern hemisphere is pointed toward the sun. So when we have winter, the southern hemisphere has summer, right? Seasons, and that's why we have them. In any case, that's how the sun appears to move across the celestial sphere, and why we have seasons, and why we have seasonal stars. Like, you can't see some stars in the summer, you can only see some stars in the winter, etc. Right? Because the sun will light up part of the sky during daylight hours, and those parts of the sky or parts of the celestial sphere will be different at different times of the year. Now, the apparent path of the sun across the celestial sphere, of course, is due to not only our rotation, but also our revolution around the sun. But the Earth actually has one more motion, a very strange thing, called precession. So the Earth doesn't only spin, and it doesn't only revolve around the sun, but also the spinning makes it wobble, like a spinning top, if you've ever seen or played with a top. And so the direction of the North Celestial Pole revolves, and that revolution takes something like 20 some odd thousand years, if I recall correctly. And so it takes a little while for it to make one of these loops all the way around in a circle. But right now, the North Pole is actually about a degree or half a degree away from the North Celestial Pole, and in about 20,000 years it'll be sort of pointed close to where it is now. But in about 10,000 years we're going to be looking at Star close to Cepheus, maybe Deneb, will be a better North Star. But right now, Polaris is a good North Star for us. Anyway, where was I? Oh, right. So that's basically how and why and where the sun revolves about the Earth. But there is another object very close by to us, one that's even closer as a matter of fact, the moon. Now the moon also kind of moves in its own way. But just as we are revolving about the sun, the moon revolves about the Earth, right? Interesting. Now it doesn't move in a perfect circle the way that the Earth moves in an almost perfect circle around the sun. Instead, the moon has an elliptical orbit. It's much more oval shaped, and the direction that the oval points precesses, just like one of the images in our image bank for the day denotes. And so the direction that the oval points precesses as the moon makes its orbit around the Earth. But also, not only does the direction that the oval points change, the tilt of the elliptical orbit also changes, right? We call that nodal precession. And the direction of the oval, the ellipse, evolving, right, rotating, we call that apocidal precession, right? And so we have a very complicated kind of orbit. The moon isn't always, at its maximum distance. It doesn't always get to its maximum possible distance, right, because of this crazy topsy-turvy, constantly evolving kind of orbit. It's sometimes closer than others at some points, and sometimes it's further away. And consequently, that means sometimes the moon is brighter when it's a full moon. We call that a supermoon, right? Sometimes it's real close, and sometimes it's real far. The maximum distance is something like 400,000 kilometers, and the minimum distance is closer to about 350,000, right? But it's for that reason that the full moon isn't always the same size, right? Now, the moon is much, much smaller than the Earth, right? So much so that when the moon goes into the Earth's shadow, it's very easy for the Earth's shadow to swallow up the entire moon. Now, once upon a time, people realized, probably thousands of years ago, the ancient Greeks, the Chinese too probably, all realized that the shape of the Earth's shadow on the moon, what that means is that because the shape of the Earth's shadow is round, that the Earth's curvature, the actual shape of the Earth, has to be round. And people knew this a long time ago, long before people founded this crazy flat Earth society. Okay, in any case, let's talk a little bit about the phases of the moon. And maybe I'll perform for you the moon kata. Alright, if you look at the moon in the sky, right, it's, very small. It's actually about 1/2 of 1 degree. If you look all the way to your right and then all the way to your left, if you draw a line all the way across the sky from your right to your left, that's 180 degrees, right? And the moon is about 1/2 of 1 degree. Now, strangely enough, the sun is also about the same size, and so we can have, these crazy eclipse events when things all line up just right. but more on that in just a moment. Let's talk a little bit about the phases of the moon. Now, the moon revolves around us, and we revolve around the sun, right? And so sometimes the moon and the sun are near each other in the sky, and sometimes they're far apart, because as we are moving around the Earth, or as the Earth, is moving around the sun, the moon is also moving around the Earth. How long does it take for the moon to move around the Earth? For it to go through one complete cycle of phases? About 28 days, right? And that's where the term month comes from. And so it takes almost 30 days, about 28, for the moon to go through one complete cycle of phases. Now, you can look up at the moon, and if you see how much it's illuminated, you can kind of tell where it is in its orbit, or where the sun should also be, right? That should be pretty straightforward. Obviously, if you look up in the sky, and you don't see the moon at all, but, just a week ago, you saw that the moon was getting closer to where the sun is, that must mean that the moon is near the sun, and therefore not lit. But if the moon is all the way on the other side of the Earth, right, we're going to see its entire face lit up, because the sun is going to be shining its light on the moon. And that's the only reason that we can ever see the moon lit up, right? The moon does not generate its own light or heat. The only way that we can see it is because it's lit up by the sun. Okay? So, there are two sort of really easy configurations, and you can kind of start from either one, and that's where the moon and the sun are close together in the sky, right? And so you can't see the sun at all, or sorry, you can't see the moon at all, because the side of the moon that's lit up is facing the sun, and that's facing away from us. That's the new moon, right? And then there's when they're on opposite edges of the sky, on opposite ends of the sky, right? You have the full moon, right? Because the sun is lighting up this side, and if the Earth is my head, then the sun over here is lighting up the side of the moon that is facing us. And so we can see this face all lit up, right? That's a full moon. Now, the moon moves around us the same way that we rotate, the same way that we revolve about the sun, the same way that everything in the solar system moves together. Pretty much all objects, even the trans-Neptunian objects and dwarf planets and everything, all go in the same direction. Now remember we said that the sun rises in the east and sets in the west because the Earth is actually moving the opposite direction from west to east. Well, not only does the Earth rotate that way, but the moon revolves about us that way, and we revolve about the sun that way. Everything in the solar system goes in that direction together. Okay, everything moves in that sense, that west to east sense. Okay? That, of course, is because everything that made up the solar system came out of the same accretion disk, out of the same cloud of particles and matter. But we'll talk a little bit more about that later on in the semester when we discuss accretion disks and star formation and the origin of solar systems. Suffice to say that the moon starts in one place and goes in this sense and takes 1 month to make a complete revolution. Okay. Now, how can you track where the moon and the sun are relative to each other over the course of a month? And in order to do that, myself and some of the other instructors that I've worked with have constructed what we call the moon kata. And for those of you who have ever studied martial arts, when you practice form, they call it kata. At least that's the Japanese word for it. In any case, I'm going to have to reach up over my head here probably, and so I'm going to unbutton my jacket. If you'll excuse me. So there are two major players in the moon kata. There is the sun, and you can tell it's the sun because of its bright sun rays, and then there's the moon, right? Okay, so we're going to start here, at this phase. Now what phase is this? What phase could this possibly be? Well, the moon is near the sun, right? So this has got to be the new moon, right? The sun here is going to light up this side of the moon, and so we don't get to see it. We're going to see the dark side, right? Okay, now this is going to move this way over the course of the month, right? 2 weeks later, it'll be here, and this, the moon will be lit, right? This will be a full moon. I'm going to switch hands now, right? Okay, here's the full moon. And then we'll progress this way, okay? That'll be one lunar cycle, okay? We call this the new moon. As the moon approaches this way, we'll start to see just a little sliver of it lit up. And when the moon is less than halfway lit up, we call that a crescent moon, because obviously it looks like a crescent. You've seen it many times, right? Okay, now when the moon is appearing to get larger, we say it's waxing. And if it's less than halfway lit up, it's a waxing crescent, okay? So the moon is a waxing crescent, waxing crescent, waxing crescent, until the sun and the moon are 90 degrees separated, at which point this half of the moon is going to be lit up relative to us. We call that first quarter, okay? So we got first quarter. And then after that, the moon is going to appear halfway, more than halfway lit up to us. If the moon is between halfway lit up and all the way lit up, we call that a gibbous moon, right? So we're going to go from waxing crescent to first quarter to waxing gibbous, until finally the sun and the moon are at opposite ends of the sky from each other, right? My head, of course, is still the Earth. And we have the full moon. Okay, now I'm going to switch hands again. We're going to progress forward here. As the moon appears to be getting dimmer, we call that waning. And now, because the moon appears completely lit from here, right? We've got it waning. It's going to appear to get smaller. So this is a waning gibbous, right? Waning gibbous, waning gibbous, waning gibbous, until finally we're again at 90 degrees separation. This is third quarter. And the moon appears halfway lit up. This half is facing the sun, right? And so it appears halfway lit up. And then we have a waning crescent. Waning crescent, waning crescent, waning crescent, until finally we are back to the new moon configuration where you can't see the moon at all. Okay? Now that's just the basics. Now let me tell you what the moon kata is useful for. Okay, if you know what phase the moon is in, like if you look up and you see, you look it up, right? You go to one of the Navy charts or whatever, you just Google it, it'll tell you what phase the moon is in, right? Now if the phase of the moon is first quarter, right, you know that they should be 90 degrees apart, right? Like one straight up and one straight to your right or something like that, okay? If it's first quarter, that means the moon is going to be to the left of the sun by 90 degrees. Now what is this good for? Well, 90 degrees, how far is that in travel time? Well, if the sun is directly above you like this, what time is it? It's noon, right? Here in the northern hemisphere, if we're looking up to see the sun, we've got to be looking southward, right? And so that means that the moon is going to be here on the eastern hemisphere at noon. And then some hours later, as the sun sets, the moon rises, right? Until finally about 6 p.m. or whenever it is that the sun sets, the moon will be at its highest point in the sky, right? And then, 6 hours later, at midnight, when the sun is at the lowest point, the moon will be setting. 6 hours later, at about 6 a.m., the moon will be below the horizon, but the sun will be rising in the east. And then 6 hours later again, the sun will be in the middle of the sky because we've gone 24 hours and it's noon again, and the moon will just be rising. Right? Okay, so obviously the sun and the moon move together during the new moon. They're 90 degrees apart. When it's first quarter, they're 180 degrees apart during the full moon. So when will the full moon be highest in the sky? When the sun is at the lowest point, right, at midnight. And you can do this for any configuration, of course. What time will it be when the third quarter moon is highest in the sky? Well, third quarter is 90 degrees to the right of the sun. And so the sun will just be rising when the moon is highest in the sky. It's about 6 a.m. or something like that, right? In any case, that is the moon kata. And it's a useful sort of back-of-the-envelope kind of calculation to show where the moon should be relative to the sun at different times of the day, at different parts of the lunar phase cycle. It won't tell you exactly when the sun rises or the sun sets. Of course, that's a little bit different depending on the time of the year, right? Excuse me. How much of the ecliptic is in the sky and how much of the lunar orbit is actually in the sky. Remember, the moon has a very funny kind of orbit. Sometimes it's up to 400,000 kilometers away, sometimes it's only 350,000 kilometers away, and so it appears larger, and so on. Right? It's got a really funny kind of orbit. Sometimes it's more northward, sometimes it's more southward, because it does this funny oscillating kind of thing. But essentially, you can kind of get a rough idea of where the moon should be at what time of the day if you understand what phase it's in. Okay. We talked a little bit about the shape of the Earth's shadow on the moon. And the Earth's shadow, of course, is round because the Earth is spherical. Well, it's not a perfect sphere, but it's round. And so the Earth's shadow on the moon is also round. But the Earth's shadow is much, much larger than the moon is because the Earth is much, much larger than the moon. And so it happens pretty often that the moon goes completely and totally inside the Earth's shadow sometimes. And so, first of all, for that to happen, what phase does the moon have to be in the Earth's shadow? Well, if the sun is over here, and the moon is over here, right, then the light from the sun can get blocked out by the Earth, and the moon can be in its shadow. That's full moon, right? The sun and the moon are at opposite ends of the sky, right, relative to the Earth. So, sometimes, during the full moon, the moon will go completely into the Earth's shadow. Now, that doesn't dim it out completely. As a matter of fact, because the Earth is so massive and there's such strong gravity, some wavelengths of light will bend just the slightest bit and actually hit the moon. And those happen to be the wavelengths of the light that are closest to the color red, right? And that's why sometimes you have these blood moons, right, during a total solar eclipse, where they look kind of reddish-orange. It's because the reddish-orange light is bending around the Earth to hit the moon when it's in the center of the Earth's shadow. Interesting, right? We call that, of course, a lunar eclipse. Now, lunar eclipses, of course, are not the only kind of eclipses that we see, although the other kind, the solar eclipse, is much more rare and much more difficult to get a look at. Why is that? Well, the Earth is very large compared to the moon, right? If we were to try to make some kind of size comparison, the Earth would be like this, and the moon would be maybe, like this, very small in comparison. And so the light from this object is only going to shed so much shadow on this larger object. And because the moon is kind of far away, and the sun is actually much larger than both of these combined, right? The sun is huge. And so the amount of shadow that the moon can shed on the Earth is very tiny. As a matter of fact, the angular size of the moon, how large the moon appears to be in the sky, is only roughly about the size of the sun. When the moon is at its farthest away point, when it's farthest away from the Earth, that 400,000 kilometers, it's actually too small to cover up all of the sun. When it's closer and appears bigger, it can block out more of the sun's light here at the surface, right? And so sometimes you don't even get a total solar eclipse. But sometimes you do. And so if the moon is close enough that the darkest part of its shadow, what we call the umbra, the part where it blocks out all of the direct sunlight on the Earth, if you're standing in that tiny little patch, which is only like a few kilometers across, if you're standing in this tiny little spot on the Earth, you can see the entirety of the sun get blocked out by the moon. It's called a total solar eclipse. And there was just one not that long ago, a few years ago, that went over across the North American continent. And if you got to see it, it was pretty awesome, right? That's pretty dope. That was the only total eclipse that I've ever seen. But in comparison to all the images and things that I've seen of total solar eclipses, it was much more phenomenal. You could see, lots of solar flares and prominences coming out from the sun, and it got real dark and cooled off real quick. Only for a few minutes, of course. But getting under a total solar eclipse is pretty interesting. It's not like any other experience you could really have here on the surface of the Earth, right? It doesn't quite turn to night because obviously the sun the sun has still lit up the entire sky, right? The sky is still blue. And also, if you look kind of in the horizon in every direction, you can kind of see that there's light beyond, like in the like just off the other side of the horizon, So it's dark where you can see, kind of, but not that dark. Yeah, it's pretty interesting. In any case, that only generally lasts for a few minutes at most. And sometimes it lasts even shorter than we might expect, because the moon may be moving away from the Earth or moving towards the Earth, and so it goes from not being able to cover up the sun to being able to cover up the sun, or from covering up the sun all the way to not being able to cover up the sun anymore. We call that a hybrid eclipse. And if the moon is too far away from the beginning of the eclipse to the start of the eclipse to cover it up, such that direct sun always gets to the surface of the Earth, even if you're directly under where the moon's shadow is, we call that an annular eclipse. Annulus from, I believe that's Latin, meaning a ring. Because, just like the image in today's image bank, there will look like a ring of sun around the moon, right? A ring of light, because the moon is too far away to cover up all of the sun's direct light. Now, for those of you who were not fortunate enough to view how shall I say it, the total solar eclipse that went over the North American continent, I've put a link to a total solar eclipse on today's lecture page with the image bank. So you can go ahead and have a look at that. go ahead and watch it. It's only a few minutes because it doesn't last that long. You know, the Earth rotating means that this tiny little spot that's only a few kilometers across moves across the surface of the Earth, right? The moon doesn't stay in front of the sun that long. All those things add up to, oh, you only get a few minutes of totality. But it goes from being real bright to getting real dark to getting real bright in just a few minutes. And so if you haven't seen it yourself, I highly recommend that you watch the video. It's pretty interesting. So much so that lots of people spend their entire lives chasing eclipses. And that may be a kind of a severe expenditure of time and effort, but hey, you know, whatever makes you happy. In any case, please ask me any questions about today's material if you have any questions on it. And if not, then I hope you have enjoyed today's lecture as much as I have giving it. Please make sure you review today's material thoroughly for the quiz next time.